Every story, there comes a moment of confusion, a point where direction fades and uncertainty takes over. This is one of those moments. Asan na kaya yun? Dumaan na ba ako dito? Teka, ba't ako nandito? Guys, sino kaya to? Grabe talaga, inasar pa talaga ako. O kaya mahahanap yung building na yun? Oh, sino naman kaya to? I swear, pag ako talaga inaasar pa nila. Campus navigation app? Matry ko nga.
Hello everyone, today I'm going to demonstrate how our campus navigation system works. As we can see, we have buttons on the top like add buildings and etc. Also, we have canvas here with a simple map of CSPC. This is a session overview. This is zoom up, zoom in, and reset button. We have our buildings represented by these nodes. These nodes are used to select the building you desire. For example, suppose that I am at gate 1 and I want to go to green building. As I select the nodes and search for the shortest path, it will display the road I need to take to get to the building. As simple as that. You can try this yourself as many times as you want. Next, I'm going to introduce a feature that encourages creativity among our students. This section of the tutorial lets you create your own campus map. To add buildings, first, click on the empty space in the canvas. Click on the add building, and finally, add the name of your building. To add the pathway, you need two buildings. Next, select the first building and the second building, then click on the add pathway. Now, no time being Run your lost. Creativity well. Hurry to your as many buildings and pathways as you want. Now, if you want to test the routes in your map, select an initial building and the goal building. The program will tell you if a building is unreachable from that initial building.
Ayos, alam ko na kung saan. Uy, hinintay mo pala ako. Uy, andyan na ka pala. Oo, maraming salamat sa'yo. Walang problema. O ito, handshake tayo para bros tayo. Liga na. Salamat, Navia.
So now we will delve into the Python implementation of our campus navigational system. So just a brief overview of the system. We decided to display the system visually as a web page, and then we used Django for the backend, and then for the front end we used Next.js. So for this implementation or this video output, we will only be focusing on the graph operations, which will be found inside the backend and inside the campus app, and then here in services and then graph.py. So now let's just start first with our headers and then our imports. So at the very top, we imported annotations from the future dunder method. This just essentially helps in type hint referencing. And then the next is from data classes. We imported a data class. This is a decorator. As you can see, it is used here in line 10. This automates the boilerplate for constructing simple classes used to hold data like wrapper, representation, and then etc. etc. And then the second import, we imported heap pop and then heap push from heapq. So heapq is it essentially provides a binary mean heap implemented as a list, and then we imported its methods, heap push and then heap pop. So heap push, this adds or pushes an element, and then heap pop, this pops the smallest element. This will be useful for the Dijkstra's algorithm for the priority queue. And then below it is we imported type hints. This is just used all for type hints and for readability and static checking, which is important for this project. And then the last import is this allows to utilize Django's ORM models that we have created. So we have created a model for a building and for a pathway. This is our graph nodes and this is our edge models. So now we will head on to our class, this path result class. This is just essentially a small container object returned by the shortest path and the reconstruct path here, and then the reconstruct path. So we only use this to keep the return values tidy and somewhat descriptive. Now moving on to our first function, which is the build adjacency. This creates an adjacency list. So what it does is it takes an iterable of pathway objects and it builds an adjacency list, which here it directs it pipes it into a dictionary, mapping the source ID to an integer, and then the list of target ID, and then distances. This is used for representing a directed weighted graph. So edges from our source ID to our target ID is appended with weight distances. Now for our shortest path function, this is where we implemented a Dijkstra's algorithm. So this let's go delve into this from the very top to the words to the bottom. So if start ID is equals to end ID, it tries finding if the buildings exist, otherwise it will return none, and if it found, it will return the path result and then the building and then its start ID. And then here in if not building that objects filter, this is just a quick validation to ensure that both the start ID and then the end ID actually exist inside the database. Below that we have an adjacency variable. This helps loads all the pathway objects from database into memory, and then builds adjacency using our function above. Now here in distances, this essentially holds the best known distances from start to each node. So we initialize it start to 0. The previous one, this will be used to reconstruct the path of the previous node to its parent node, and then the visited will hold all the nodes whose final shortest distance is known, or if we pop that, then that means that we have already visited that node. And heap, this will store the priority queue of distance node, and then it is initialized with 0 as the position and then its start ID. Now here we have a while loop. So this says that while heap, we pop the node with the smallest tentative distance, and then we skip already visited nodes, and then if the node is not visited, it will be marked as visited, and then if we reach the end ID, we can reconstruct now the path immediately and then return it. Here inside the for loop, this is a sort of a relaxation step. It iterates through neighbors and then compute the tentative weights or distances, and then it updates the distances and previous when shorter path is found, and it will push the improved estimate onto the heap. Here it will return the distances. It will return as infinity if there is no neighbor discovered. For our reconstruct path function, this just build the ordered building objects. So this reconstructs the path of node IDs by walking previous pointers backwards from end ID to start ID. So the chain becomes an ordered list of node IDs from start to end after the reverse. Here in buildings variable, we query the database for building objects and then with its matching IDs in chain. This builds a mapping ID to the building, so we can reorder them back into a chain order. Here for our isReachable function, so this just checks if one node is connected or can be reached from another node. So this uses depth first search. Since we are using weighted nodes, we utilize the depth first search instead of breadth first search. So essentially, if start ID is the same ID, it will if the ID is same, it will just check the existence in the database and then return a boolean if it exists. Here in adjacency, it builds the adjacency and prepare the depth first search stack. So we have a while loop. This is just a classic the first search. We pop the node that is and then mark it visited. Then for each neighbor, if the neighbor is the end ID, it will return 2. So it is meaning that it is reachable, and otherwise it will just push a neighbor to a stack to further explore. If the DFS finishes without reaching the ID, it will return false, meaning there is no path or it is not reachable. So for our final function, the get full map, this just exports all nodes and then edges to the front end. So we query the database for all the building objects and all pathway objects, and then it will get the related building objects in the same query. It will now then return a JSON serializable dictionary with buildings and then pathways and its respective model attributes. That is all. Thank you.